Let's start with Numpy today. It's a library, Python library, which helps us for many of the basic scientific calculations, and it's also used in data science, computation, and stuff like that. So the basic use of NumPy, or the basic functionalities of NumPy, are you can store, you can process multi-dimensional arrays. So when I say multi-dimensional arrays, it can hold 1D, 2D, 3D, and we'll see what is 1D, 2D, 3D, and we'll see how to store them. So, and also the it can help, or we can perform operations or computations like linear algebra operations, addition, subtraction, multiplication, matrix multiplications, and Fourier transforms on those matrices, and etc. So, I'll also show you how all the images which we see, all videos which we see, are nothing but numbers, are nothing but stored matrices. So we'll see that, and we'll understand how we can use NumPy to understand the basics of image processing, digital signal processing, basically. So, and when I say NumPy can be used for storing arrays or numbers and forms of matrix or something, so you can tell me there are other options like lists and all. So there is one drawback in lists, so that is lists are slow. You can ask me why. So there is this problem with lists. So it has different kinds of information which has to store, which has to be stored when you want to store a single number. For example, its a size, its a count, its object type, its value, and stuff like that. And each of these, whichever I mentioned earlier, will have at least 4 bytes of 4 to 8 bytes of memory just to store one number. So basically, it is like it is 24 plus 4, that is like 28 bytes just to store one number. So, and if the data is more, if the processing data is more, it obviously takes more time to understand that number. Whereas in NumPy, you'll have a fixed type of storage here. So you'll get to store one number in 8 bit, that is 1 byte, or depending upon your number size, your size of number, or your, I don't know, uh, your number. For example, if you are storing until 16 or something like that, it is fine with 4 bits also, or something like that. But if your number is more than that, if your number is more than 16, or not as in 16, it is 15, until 0 to 15 you can use 4 bit. And as the number grows, you have to take more bits to represent that. So here in NumPy you have less number of bits to process to understand a single number. That is one reason which makes NumPy faster. The one more thing which list one more thing which makes list slower is the storage, the way the lists, the numbers stored in lists are stored. So they are randomly stored in the memory storage. So when they are randomly stored in the storage, so each value gets a different pointer to point out, acha, this is this number, this is where it is located, and all. So but whereas in NumPy they are stored continuously, that makes you to give only one pointer. So you all you need is one pointer to find out the rest of them. So you can for example, I have 1 2 3 4 5 until 10. So I'll give a pointer for 1, which from which you can tell where is 10 located. For example, 1 is located at 50th location, so obviously 10 will be at 60th location. So you can find out like that. So you don't have to give pointers for all the values. That is where the data consumption or storage consumption is less in terms of NumPy. So the processing is faster. So if I am saying the lists are slower and NumPy is faster, so if I say NumPy is 50 times, 50 folds much faster than lists, I'm not exaggerating, it is in that. So it is that. So there are things you can do in NumPy which you can do in lists also. That is, you can add, you can not add and add. So you can insert, you can delete, you can append, you can concatenate different arrays. So, and also there is one, not one, there are many other stuffs, other cool stuffs you can do in NumPy. For example, multiplication, matrix multiplication, which is much harder if you want to do in lists. And there are other mathematical uh, functions which you can apply directly in NumPy, which is much harder in terms of lists. So that is why, as I said, that is why it's kind of base for scientific calculation, which is, so they built this library in that mindset. So that is that. And uh, you might have seen the working environment of MATLAB. So this all these functions available in NumPy are in MATLAB also. So you can use this as a substitute for MATLAB. And as I said, all these data is being collected and all. So you can use this for machine learning too and data analysis, obviously. So let's see how images are stored. So I told images are stored in terms of numbers, matrix basically. So images are 2D matrix if you are talking about grayscale images, as in. So if you take a colored image, it is three layered image. So sorry, three layered array, that is basically 3D. It has if you want to understand what is dimension, it is basically the same dimension what we use in mathematics, that is 1D, 2D, 3D. If I say 1D, you have only in one direction, so you get numbers varying in one direction. If 2D, that is you have x and y axis too. If you have 3D, if I say 3D, it is x, y, z. And if I say 4D, I don't know how to say it, but all these XYZ varying with respect to time. So the time is the fourth dimension. So on. The varying thing, or which something else makes this dimension above this dimension. So it is a different. So yeah. Okay then. So let's see how NumPy can be used for image processing, and how images are stored as numbers and stuff like that. So there is this library called as PIL, which is the most commonly used for image processing. So let's start with importing it. So I'll call from uh, spelling from PIL PIL PIL. Let's import image. So this is uh, okay. So it is just saying we have imported it and not using it. I'll use. So it doesn't understand that. So next, let us import. What do you say? My NumPy. I can't keep writing NumPy every time, so I'll assign NumPy for something else. So, and commonly it is used as NP. So let us go with that. Import NumPy as NP. So now I have an image. Let us see what is that image. So this is my image. Come on. So this is my image. So I have this image, a beautiful error image. So on my desktop, I'll call this image by using let's call something else. Let's call image from PC, and that's, you can call anything. I'm just giving a number. It's a variable, and I prefer giving my variables a good name so that I can remember why I am using that variable. So, and np is NumPy, which I have referred it as well. So np dot, so you can see there are so many options in NumPy. So I'm using np for an array. So array. So that array, here it goes the values of the array which we want to store in image from PC variable. So, and I want the values that the image is having. So I'll call image from pil dot, so open, so let's open that image. Okay, where is that? No, file information. This is where it is. So let's go and paste. I There is a dog barking. So let's go and put a forward slash forward slash. So the name of that error.png oh doggy png. So the value of the numbers of that error.png image will be stored in image from PC. So let us run and see the values. So image, I think I chose a very long. Let's see. There you go. These are the values that are stored that the image is being represented by. So this is how you use those values to manipulate, to store, to compress, to encrypt, and stuff like that. So let us understand different things that NumPy can do. That is that is basics of, oh god, that is basics of NumPy and the functionalities of NumPy. After that, we'll go later in the end. We'll compare MATLAB and NumPy. The one thing which I kind of hate in NumPy is that each and every time you have to write np.array, which is kind of taken for granted in MATLAB. So that is there. So cool, we are cool. So let's start by import, import NumPy as np. So you can give anything. Np is popularly used. So if NumPy is not installed in your system, so it shows an error. So to install NumPy, you can go to your terminal command window and just type pip install NumPy. So if it is not installed, it installs it installs after this. So if you're using Conda, so it will be Conda install. If you're using pip3, so it will be pip3 install NumPy. So it goes like that. So after that, let's start creating an array. So let us give a name A for our array. A np. From np, I need an array, and all arrays are written inside a square brackets. So 1, 2, 3. Let's go like that. I want to print. Let us see. So you can see it is just one dimensional. That is, it varies in one direction. That's it. So if you want to change it into multi-dimensional or two-dimensional, that is, you'll have a nested array kind of thing. That is 1, 2, 3, comma 4, 5, 6. So this is 1, 2, 3 as in first row, 4, 5, 6 is in second row. Similarly, all these are int type. If you want float type or the decimal type, you can write 1.2, 1.3, 3.3, something like that. So you can see the changes. After that, if you want three-dimensional is two-dimensional is collection of one dimensions. Three-dimensional is collection of two dimensions. So let us take this and nest this inside a square bracket. Simply I can simply I can do 88. Let us do 88. See, so this is three dimensional. This is the first layer or first layer. This is the second layer. In the first layer, first row, second row. Second layer, first row, second row. So what is that? Now there are a couple of things we can do when we have an array. For example, let us see the dimension of this A. So what I'll do is I'll type A dot din and gives me three-dimensional. So similarly, I can do A dot shape. It is 2 cross 2 cross 3. That is two. There are two matrices in two different layers of 2 cross 3 matrix. So of the size 2 cross 3 matrix. So there is something you can see about A dot size. It gives total number of elements. You can see 2 into 2 into 3 is 12. So if you want to see the type of numbers and type of elements in that array, you can write A dot D DYP data type. So it is float. If I change them, to int, okay. So run before that. Now I'll type A data type. So it is int 32. That means you can have, or there are 32 bits required to represent each one of the numbers present in that array. So sometimes you can specify, if you want to specify key, I just need int 16, so you can specify that. Let us see. I'll make this 8 again, and after this I'll write dtype equals to, I need int 16 because I think int 16 will do it, but let's make this 7. So int 16. So run it and A dot A data. It gives int 16. Obviously we have written int 16, so it has to give int 16. So that means int 16 is how many bytes? 2 bytes. So 8 bit is equals to 1 byte. So int 16 2 bytes. So you can see what is the total memory used to store this array. So that is you can do it by A dot n byps 24 bytes, obviously, because there are 12 elements you saw in the size, multiplied by 2 bytes for each, that gives 24. So After that, what can we do? We can write a dot item size. So that is each element is item. So what is the item size? What is each element's size? What size is each element occupying? That is 2 byte here. That 2 is having a unit of byte. You can get that 24 by something else also. That is a dot int, not int, b type multiplied by a dot item size. What did I do? So not data type was it? Right, size a dot size into a dot item size. It is 24. So for the one on the same. So now what else? What else? What else? What else? Okay, so let's start with indexing. So let us start indexing with 2D. Then we'll go to 3D. There is one bracket extra. Anyhow, I don't want this. I'll create new one. First row, second row. Let's just give the name as 1, 2, 3. Similarly here, give 4, 5, 6. So it is okay. Let's just make it 3 cross 3 then. This is I think 4, 5, 6, 7, 8, 9. Okay. Print A. You can see. So first row, second row, third row, and this is first row, first column, second column, third column, so on. So here indexing starts by 0. That is, if you want to access 1, you'll have to write. Okay, I'll tell how we have to write. That is A. From A, I need the first element, that is 0, 0. That gives me 1. For example, what else can I do? For example, I need something else. Let us assume I need the middle term, that is 5. That is obviously 2 comma 2 if you are assigning 1. So it is 1 comma 1, 1 comma 1 gives me 5. So, and there is also negative indexing. So that means if I give minus 1 comma minus 1, it should give me 9. That is minus 1 represents the last element. So last row, last column. That is 9 obviously. Okay, let us start. What else can we do? Let us assume I need the first row. So this first while indexing, the first number is rows. So I need the first row and all columns. So I'll write all columns. This gives me see, this gives me first row, all columns. Similarly, I need first column, all rows. So I'll write first column, all rows. I'll get first column, all rows. Boom. So next, let us assume, let us create array, linear array, or I must say 1D array for better understanding. 3, 9. Okay, so if you see a dot n dimension, it is 1D. So let us assume I need numbers after 4 until 9. So what can I do? I can do is a dot, not that, brackets, I need from 4. So 4 is actually 0, 1, 2, 3. 4 is 3, third, what do you say, element, or it's the index of 4 is 3, and I need until this thing. It has to give, it gives until the end. So if you are specifying, I need from here to here. For example, I need from, I'll just make it from third position, or third, from 3 I need until 9. What I'll do is I'll do until 9. So 9 is excluded. No, 9 is not excluded. Cool. So now I can write, I need in steps of 2. It gives me in steps of 2. So that is how this is starting value, this is the end value, this is the step size between those two numbers. Oh no, there's something I forgot. Not forgot, I missed. That is 9 is 9 is 10th position, so I have to write 9 is in 8th position, so it excludes 9. It excludes 9. So it includes the starting point, but it excludes the ending point. And if you want step size, you can play with step size. In 2D, we had 2D. Let's go back to 2D. Something else I need to say about 2D. In 2D, for example, I need to access the first set of things are rows. So I need to access one, that is okay. And columns, I need columns from 1 to 2. So there's that thing. I could have just done something else, but it gives, so from which row to which row do you want, and from which column to which column do you want. So let us take an example key. We want to replace a number in our array. For example, I have to replace that 5 with 112, let us say. So I'll call 5 by its location, that is 1 comma 1, and I need to replace this with 112. So there you go. So let us print a, boom. So your 112 is in 1 comma 1. Come on, come on in. So okay, so this was something about indexing, and how can we call, how can we replace, stuff like that. So let us see about some inbuilt matrix or arrays. So we know all zero array. We can have a all zero array. Let us assume I need an array. I think I can zoom in. I can zoom in. This is not zooming in. Okay. Anyway, so I need print a. I need np, so we know this. Okay. So np dot zeros, zeros, zeros of the size 3 comma 3. Okay. Data type not understood. Cool. got to put parentheses. Okay, 3 comma 3 zeros is presented to. So let's go with we got zeros, and let us say all ones, all ones. So there is this one function. I feel it is kind of useless, but you can use it somewhere else. For example, I have full. So you can fill this whole matrix. Just take a different dimensions, a different size, 3 cross 4, full with. Let us fill this with 112. Why not? Come on. So it's 112 everywhere. So I think you could have done the same thing with ones. 112 into this thing. It was 3 cross 4. So it still gives the same answer. If I want comma d type, it is giving me a float there. If you see, d type is equals to int and 32. Should work. See, you can do that, but well, we have they have something called as full. You can use if you want, and we have full alike, full alike. So for that I need an array. Okay, let us take this only. I think there's one bracket missing. Let us make it as 3 plus 4 only. Okay. Now let us call another array. Okay, that's B. I need full like A, and you see I need a value of 112. Let's see. I didn't print B. Okay. See, you get B. So there is this and there is that. There are things like identity matrix. You know what is identity matrix, don't you? Okay, so I need identity matrix. I'll then take T. Identity matrix is a square matrix, so you won't have to write the full dimension. It takes 3 means 3 cross 3. So let's see. See, it's cool. You get it. Okay. Okay, there is this. Okay, let's go back to array, and sorry. I'll write 1, 2, 3, 4. Okay, boom. Yeah. So there is this option called as repeat. I'll call b is equals to mp dot repeat. And spelling of repeat. Repeat. I need a to repeat 3 times. And there is only one axis, so that is axis equals to 0. So let's try. Didn't repeat. Oh shit. Why am I not printing B? So print B 4 times. Now, for example, I need this one below the other. So what will I do? I'll do I'll make it a 2D by just nesting it in a square bracket. Let's go like this. Let's print B. It still didn't work. So what should I do? Axis 1. Okay. Now let us try 0. I don't know. Yeah, it should work. 4 is a 0. See, it gives one below the other. So you just have to nest that array. Then what else can we do? Huh. Okay. This is an interesting thing. Let's see. So this means there is an array A. I don't need a nested array. I just need an array. An array A which is being copied to B. This is what it does generally. Let us print A and B both. Control C, Control V, A. Cool. So you can see both are right. So now if I do this thing, B of I want 3, so B of 2 is 3 is equals to, tell me something, I'll take 1 and 2, so let's put the thing here. I'm replacing 3 with 112, so now let us see the magic. You see, even A is being changed. That means A is not copied to B. Here A is just B. Both are same. So to avoid this, or if you want to copy the A into B, you can do is what you can do is dot copy. That's it. Simple. So now let us see. See, A is A and B is changed. Simply because we changed it for obvious reasons. Okay, so I have A, I have B. What else I can do? I can do many mathematical operations. Like that is the thing which Numpy stands out with respect to lists. So let's see. For example, I need A plus 2. So it adds 2 to each element of the array A. And then if I want A into 2, if I want A to the power 2, you can see the data type being changed because it initially was int 16. Okay, let us see that also. A dot data type. Oh, it's in 32. I don't know why it is showing you that. Okay, let us see. Let us do something else. I can do. I have B also, right? So A into B, element wise multiplication. A to the power B, that's big number. A divided B, element wise division. And what else? You can have a sine, cos, or trigonometry functions. For example, I'll go with A. Np dot tan. I'll go with tan. Tan is a good thing. You can hear birds chirping, you can hear dogs barking, and you can hear me talking. That's good. I need A. Tan of all the values in A. See, that gives 10. So, I don't know. Okay, let us see. Fine, I think, 1 second, sine of 3.14. Okay, all these things are radians. And, for example, if I want to multiply the matrix multiplication, so all I need to do is, you can't do this thing simply in lists because it requires certain lines of code. It's boring. So we'll stick with Numpy. So for any two matrices to be multiplied, the columns of the first matrix should be equal to rows of the second matrix. So what I'll do is I'll create a 2D matrix of size. Okay, of size 4 construct. Okay, so this is basically 2 cross 4. Now I have to create 4 cross something. That's bad. I can do is copy, paste, comma, paste. This is basically 4 cross 4. So number of columns and this array is equals to number of rows in the B vector, B array. So okay, let us try and print them. Okay, print A, print B, run. You can see it's 2 cross 4 and it's 4 cross 4. So uh, all you need to do to multiply that is just give a different name. I'll give mat mul a b, and why that much big. Give c, c np mat mul, send the first matrix and second, then range c. Okay, see, I don't know whether it is true. It is true because it's programmed to be that. So nothing else, nothing else. Done. Okay. Let's go back. All these stuffs are from mathematics. So that is done. That is done. That is also done. Let us take this down. So it's now print. Okay, I'll call you A. So we did copy shape. Let's run this. Okay, I'll call A shape. Let's take cross. So now let us reshape this. I can reshape this as A right here. A is equals to A dot reshape. So all you can do here is, so 3 4s are 12, so you can break 12 in many different ways. That many ways you can reshape it. For example, I can write 12 as 1 into 12, right? So I'll write 1 comma 12. So let us run this. See, let's write 12 comma 1. It gives you column vector. So as long as you have the multiplication correct, then there will be no error. What if you write something like 3 5 3, which is 15, which is not 12? So let's see. cannot reshape. Size is 12, shape is 15. That is just wrong. Okay, so you can do it as 2 comma 2 comma 3. 2 into 2 into 3 is 12 again. So run, see, that's it. That's reshape. You can do flatten, you can rotate, you can do stuff like that. Fine. But there is this thing. For example, okay, let us go back to uh, okay, let us do this thing. Now, this is that. If you want to find in which index a certain number is, what you can do is, let us call some name np dot where can you find a is equals to which number is repeating 5, let us say. So to print c, not a. See, that's that's in second and it's in eighth positions. Okay, so we can do like less than 5. It is in 0, 1 and 4 and 5th positions. 0 or equal to 5. See, all those things. So there is this cool stuff you can do, that is a of a greater than 5. See, you can get those positions, the numbers which are greater than 5. That is simply because in the previous example, when we had a greater than 5, you got the positions where the elements are greater than 5. That was 0, 1, 2, 3, 3, comma, 4, 5, 6, comma, 7, comma, 8, 9. Okay, these all are the places. Let us see, let us run this. To my index. What did I do? What did I do? What did I do? So, why is it showing like this? Okay, that is simply because. Okay. So you can do a less than 5. 5 objects not available. So what else can we do? We can concatenate, we can iterate, we can enumerate. So okay, there is this thing about generating random numbers. We'll discuss random number generation separately, simply because it requires a separate discussion. And that's it. And there are different syntaxes, there are different options, there are different. Huh, you can find minimum, maximum, sum of the array, for example, or to do sum. A dot, okay, run this. A dot sum. So it gives the whole sum. So I think we know that the sum of 1 to 10 is 55. So let us try that. 10. So I need a dot sum. I can get, oh come on, a dot sum. What's wrong? A built-in method sum of numpy is used. Okay. Ah, I'm missing the parentheses. How can you do that? If you add 10 here, you'll get 55. For obvious reasons, 55. So you can write min is 1, max, max, that is 10. You can do all sorts of stuff like this. And that's it. That was introduction to Python. Sorry, that was introduction to NumPy library. If any doubts, queries, etc., you can contact me through, I know the thing what people do, the thing, the YouTube thing. So let's tell you a very goodbye. Let's say bye, bye. See, I just hacked this thing. Ba -ba -bam.